Okay, so today I was originally going to get started on our second module on pipe networks. I decided I wanted to give you a bit more practice just based on how rushed I felt things have been. So what I'm going to do is I'm going to start off today by going over the example that I looked at last time in class and just complete the end part of that problem. And then for the rest of today, I have an in-class exercise for you to work on where you'll get some practice doing these kinds of problems before the first exam. So let's go back and just review the problem that we looked at last time. So last class, we looked at an example of computing the discharge from a pipeline system. So we had a reservoir and a series of pipes of different diameters. So this is kind of a synthesis problem that combines together all the things in the course that we've looked at so far, including the energy equation, the Darcy-Weisbach formulation for frictional losses, the Swamy-Jain approximation for the friction factor, and minor losses altogether. So this is a good example of a problem you might expect for the first exam. So we have a cast iron pipe that transported water from a reservoir into the air through a two-section pipeline that terminated in a rotary valve located 100 meters below the water surface. If the water is 10 degrees Celsius, compute the flow rate in the pipeline. And we've got two pipe sections, one with a diameter of 40 centimeters, that's 1,000 meters long. That transitions into a second pipe that is 20 centimeters in diameter and is 1,200 meters long. So we applied the energy equation between the reservoir and the rotary valve, so between the reservoir and the outlet. And we were able to simplify our energy equation into the following form. So this right here is our energy equation. So we have that the difference in elevation is equal to the velocity head at the outlet plus all of the head losses. And so the next thing we did was we went and we substituted in all of the different head losses into this term here, HL. So this is still the energy equation. We're just plugging in all of the different terms for the energy losses in this HL term here. Okay, so we went through, we computed the major losses. So there were major losses in each pipe section. So we have a term for the first pipe section, a term for the second pipe section. And then we computed the minor losses. So we found that we had three different sources of minor losses. We had the entrance losses, the contraction losses, and the valve losses. We were able to specify loss coefficients for each of those. And then we substituted all of those losses into our energy equation. So this here, this is all just HL. Everything in this bracket is just HL. And this equation here is the energy equation. So that's what this big equation here is. It's just the energy equation with all of our loss terms substituted into the energy equation. So we rearranged it to put 0 on the left-hand side. And then we also grouped terms by the velocities that they depend on. So these two losses here depend on the velocity in pipe 1. These 4 terms here depend on the velocity in pipe 2. And with that, we can solve this problem in a spreadsheet by basically trying to select values of the discharge that make this equation go to 0. So we're iteratively computing values of the discharge that make this equation go to 0. At the very end of class, I completed this example. So I actually have the solution up under lecture 7 notes. So this is the solution. The discharge was about 0.116 cubic meters per second. Let me just go through briefly and show the steps that I took to solve this problem, because I know I was going very quickly last time. So this is our spreadsheet. What was my initial guess the first time? Do you remember? 0.5? So let me go back and put in 0.5 for my initial guess for Q. I'm going to delete this whole thing. Okay, and I've specified all of the fixed parameters of the system. So length in pipe 1, diameter in pipe 1, roughness height in pipe 1, length in pipe 2, diameter of pipe 2, roughness height of pipe 2. Our 3 loss coefficients for the minor losses. Which one of these is uncertain, by the way? If you'll remember, one of these coefficients we actually had to guess. Kc, right? The contraction loss coefficient depends on what parameter that we did not know? Velocity. So Kc depends on velocity, so we had to guess a velocity, and based on that, we came up with a guess for Kc. So I've specified an initial guess for that contraction loss coefficient. We've also got our other known parameters, so acceleration due to gravity, the dynamic viscosity, the measured elevation difference between the reservoir water level and the outlet, pi, and the density of water at our given temperature. So here I'm just going to go ahead and compute these quantities again in front of you so you can see exactly what I did to get the answer. This shouldn't take too long. So our area, cross-sectional area pipe 1 is pi, that's cell B14, times the diameter of pipe 1 squared divided by 4. So I will paste that out to the side. The velocity in pipe 1. So this is the discharge divided by the cross-sectional area. We have our initial guess for the discharge, so let's plug that in. Discharge divided by cross-sectional area of pipe 1. For our Reynolds number, this is the diameter times the velocity times the density divided by the viscosity. So this is diameter of pipe 1 times the velocity of pipe. Actually, I'm going to use absolute value of the velocity of pipe 1 because the Reynolds number should never be negative, times the density divided by the viscosity. And if you use the kinematic viscosity, it's, you can use just d times u divided by the kinematic viscosity as well. E1 over d1, so that's literally just E1 divided by D1. FYI, I have power strips located throughout the room if you need those. For F1, we're going to make our lives a lot easier by using the Swami-Jain approximation. So this was given by, let me just go ahead and paste these formulas out to the side. So the Swami-Jain approximation for the friction factor is 0.25 divided by log 10 of E1 over D1 divided by 3.7 plus 5.74, is that right? Yes, 5.74 divided by the Reynolds number to the 0.9 power, all squared. For the area of pipe 2, it's the same deal. So pi times the diameter of pipe 2 squared divided by 4. For the velocity of pipe 2, it's the discharge divided by the cross-sectional area of pipe 2. Reynolds number again is the diameter of pipe 2 times the absolute value of the velocity in pipe 2 times the density divided by the dynamic viscosity. E2 over D2 is just the roughness height in pipe 2 divided by the diameter of pipe 2. And Swami-Jain for pipe 2, so 0.25 divided by log 10 times quantity, log 10 of quantity E over D divided by 3.7 plus 5.74 divided by Reynolds number to the 0.9 power, all squared. Okay, and if you don't have these formulas, they should be up in that completed Excel spreadsheet. I just wanted to go through them step by step. So we have our computed quantities. Now we just need to put in our objective function. So if we go back to our equation here, our objective function is going to be negative delta z plus this whole quantity times u1 squared over 2g plus this whole quantity times u2 squared over 2g. So let's go and put that in. So we're going to have negative z plus, let's do u1 squared over 2g. I'm going to put brackets around that, times the quantities that depend on u1 squared over 2g are f1 times delta x1 divided by a d1 plus the entrance loss. Okay, now we just have to do that for the other pipe. So we have u2 squared over 2g. So that is u2 squared divided by 2 divided by g times quantity 1 for the velocity head plus f2 times delta x over d. So that's f2 times delta x2 divided by d2. And then we have to add the remaining minor losses. So we're going to add kc and we're going to add kv. And I think that looks right to me. So this is our objective function. This is the energy equation rearranged such that the left-hand side is equal to 0. We want to select the value of Q such that this cell and thus the right-hand side of this equation goes to 0. Okay, so I have the whole formula up in the completed Excel spreadsheet if you want to see it. I'll go ahead here and just copy and paste this out to the side, but again, I have that whole. Okay, it's not doing it. Let me put quotes around it. There we go. Okay, so next we are going to use the solver to make this cell try to go to 0. So I'm going to go to solver, set objective D2 to value of 0 by changing variable cell C2, which corresponds to the discharge. I'm not going to put any constraints on it because I don't think we'll need them. And I'm going to go ahead and hit solve. And you should get an answer about 0.116. So that is the procedure for solving that problem. We're going to be doing, again, a lot of problems like this, so I want to make sure you get practice and that you understand this procedure. Pretty much most of the problems on the tests will involve this kind of problem solving. Are there any questions about what I did for this example? Yes. Well, so I would recommend thinking of this problem like an engineer and thinking, you know, do I need a constraint to make this work? So it's not really that there's a particular type of problem where you need to use a constraint. It's just that if it's not working, you may have to, add a constraint to get it to run. There are certain problems where you do have fixed constraints. I would say that this type of problem here, you can either account for it with constraints in the solver or with constraints in your actual formulas in the cells. So like I put an absolute value on that velocity term in the Reynolds number. Was there a comment over here? Okay. And remember that I do have those Excel sheets uploaded under lecture 7 notes. Yes. That's a tricky problem, and in general, for tests, I'll tell you what initial guess to use. It does need to be somewhat close to the answer, or else it does risk not converging. And that's just a general problem with numerical optimization. There's no hard and fast answer for that. But on tests and other evaluations, I'll tell you what initial guess to use. Yes? So I think, yes, from now on, I will tell you. I think just for any problem in this class, unless I specifically say to use Colebrook White, Swami Jain is fine to use. It's a good approximation for most of the types of problems we'll be looking at in this class. Not necessarily, because you could use Swami Jain to compute that friction factor. So when you use Darcy-Weisbach, you get the friction factor from either Colebrook White or Swami Jain, or it might be provided to you. So one of those three. Yeah, they'll be very close. Yeah. Be very close. Any other questions on this example? Okay, so for the rest of class today, I want to give you some practice working on these types of problems, specifically trying to solve for different parameters. So far we've looked at solving for the friction factor directly. We've looked at solving for the discharge. But theoretically, any parameter of this system could be a variable that we're trying to solve for. So I have an example up on Canvas quizzes. Go to Canvas quizzes, and there should be a problem called in-class pipeline problem. And let's take a look at this problem together. So for the rest of class, I want you to work with those around you to solve this problem. And for this problem, I actually want you to do it from scratch. So I'm not going to give you a starter spreadsheet. I want you to formulate and solve the problem from scratch. So here is the problem. Austin Water wants to convey 5,000 cubic meters of water per day from a reservoir A to a water treatment plant B located 10 kilometers away. So 10 kilometers here is the horizontal distance between the two reservoirs. The water surface of the reservoir A is 5 meters above the entrance of the pipe, and the water surface of the receiving tank is 1 meter above the exit of this pipe. So this distance here is 5 meters. This distance here is 1 meter. So the pipe will be laid on a 1 in 500 slope and will be made of concrete with good joints. A rotary valve will be placed at the midpoint of the pipe to control the flow. Temperature in the area is on average 20 degrees Celsius, so close to normal conditions. I want you to use Darcy-Weisbach for frictional losses. And the overall goal of this problem is to determine the minimum diameter pipe needed to convey the design flow rate. So there are a couple of helper problems on the way that will help you debug the solution if you can't get that diameter correctly. But the overall goal of the problem is to solve for the diameter in the pipe that conveys the design flow rate of 5,000 cubic meters per day. So that's a flow rate in cubic meters per day. All right, so I will come around to help with this problem. You have until the end of class to finish it. It's technically due Thursday at the end of the day, but it'd be good to finish it as quickly as possible. If you finish this problem early, you can also work on your homework and ask me homework questions, okay? All right. All right, so it's 10:15. Let me just check in with you. So who is submitted a correct answer for the first problem? So has anyone tried submitting a partial answer yet? Yes? Yes, you have unlimited attempts. Yes, so you have unlimited attempts. So go ahead and if you have answers, go ahead and okay, so it sounds like a couple of you got the correct answer for part one. Did anyone submit a correct answer for problem two yet? Okay, I got a couple. For problem three? A couple, okay. So maybe let's go ahead and I'll just I will cover the first three problems. So let's just quickly look at this here. So what are the three sources of minor losses? Does anyone want to volunteer an answer? Yes. So yes, there is a contraction and expansion. It's a specific kind of contraction. Entrance and exit losses. So there's an entrance loss, an exit loss, and a valve loss. So from that, we can compute the different sources of the minor losses. So the minor losses are going to be equal to K entrance times U squared over 2G. So that's entrance plus KV times U squared over 2G plus KD times U squared over 2G. What was the value you used for KE? So for this one, I saw a couple of people trying to compute the angle. You don't really need to do that unless it's a very sharp angled entrance. KE is about 0.5. KD is always the same number. What number is that? 1. So this is always 1. And then KV, what did you get for KV? 10. So for a rotary valve, this should be about 10. The U we compute by taking the discharge divided by the cross-sectional area. So that'll be the discharge divided by pi d squared over 4, where d is your initial guess of the diameter. So you can compute all of these minor losses without running the solver or doing anything like that. For the major losses, you can use Darcy-Weisbach. So that'll be F times delta X over D times U squared over 2G. This delta X, I get a lot of questions about the notation here. This is the length of the pipe. So this is actually the length of the pipe, which will be about 10,000. You can compute the hypotenuse of that triangle to compute these frictional losses, but it'll give you about the same answer. So if you have your initial guess of the diameter, you can compute this major loss. You can just use Swami-Jain for the friction factor. So that's 0.25 over log 10 of E over D divided by 3.7 plus 5.74 divided by the Reynolds number to the 0.9 power, all squared. So you can compute both of these without doing any kind of solver stuff. Yes. Yes. So Reynolds number should be something that you've memorized by this point. So this will be D times U times rho divided by the dynamic viscosity. So with that, I will give you the rest of the class to finish this problem. There is one more part of the problem that might cause some consternation. So that is computing the known head loss between the two reservoirs. So how can you do that if you don't know the actual discharge or the actual velocity or diameter of the pipe? So how do you know what the head loss is between the two tanks? This is a known quantity. Yeah, so the head loss is the difference in the elevation of the two tanks. So note that when you're computing the difference in the elevation, it's not equal to 5 minus 1 because the bottoms of the two tanks are at different elevations. You need to compute the difference between this water level here and this water level here, accounting for that elevation change between the bottom of the two tanks. Okay, so that's all of the hints that I will give on that. We'll give you till the end of class to finish up and come around to answer questions as needed, okay?